Okay, so welcome to everyone. This time we have Joshua Feinberg, and he's going to talk about dynamic of disordered mechanical system with large connectivity, free probability theory, and quasi-Hermitian random matrices. So thank you very much, Joshua.
Thank you,
Go ahead.
Thank you for the introduction, and thank you for organizing all this wonderful series. Okay, so this work was done over several years with, with my postdoc Roman Reiser at the University of Haifa, and there is a series of upcoming papers. Okay, this is the outline of my talk. I will introduce what I call strictly quasi-Hermitian and pseudo-Hermitian matrices. Then I will give you a realization of a physical realization of these strictly quasi-Hermitian matrices with a mechanical system, a very large, highly connected mechanical system which executes small oscillations around some equilibrium point. Then I will try, I will argue that there may be a connection to vibrational spectra of globular proteins, that the vibrational spectra of globular proteins may have something to do with our theoretical predictions from the random matrix model. As another realization of this highly connected mechanical system, I will discuss the vibrational spectra of disordered multi-segmented pendulum. I will show you some numerical results and analytical results, and also I will show you that there is a localization transition in this system, Anderson localization. And then, if time permits, in the last minutes, I would like to flash in front of your eyes some numerical plots of eigenvalue spectra of pseudo-Hermitian random matrices. This is all the work which I discussed in Bangalore 2 years ago. For completeness, I would like to mention these results, but only if time permits. So that's the plan, and I hope to stick to it. I'll do my best. Okay. So what are strictly quasi-Hermitian matrices? Okay. So let us, well, basically, in this community, everybody knows about the intertwining relation and PT symmetry and metrics and what? Did somebody ask something?
No.
Okay. So basically, what I'm showing you now is finite dimensional analogs of the things that you are familiar with. So let M and H be two n by n matrices. Let's assume M is Hermitian and positive definite. We'll call it the metric. H is a complex matrix, and we say that H is strictly quasi-Hermitian with respect to metric M if it fulfills the intertwining relation. Okay. Oops. So here I have to scroll with my fingers. Okay. So this is the mathematical meaning of that. It just says that M is the metric and H is Hermitian with respect to this metric in this inner product space. Okay. We can go fast. So now, given M, the general solution of the intertwining relation, M dagger H dagger M equals MH, is simply H equals A times M, where A is a Hermitian matrix. That's the general, if I consider the intertwining relation as an equation for H, okay, M is given, H is an unknown, then the general solution of this equation is simply H equals A times M, where A is ordinary Hermitian. Ordinary Hermitian. See example, this nice old 9-year-old paper by Yogesh et al. Okay, so therefore, given the metric, there are exactly n-square independent quasi-Hermitian matrices with respect to M. I just take all the spanning basis of this Hermitian matrices. So as you must know, the spectrum of H is real, since H is similar to a Hermitian matrix small h, square root M, A square root of M, or if you like, the similarity between capital H and small h is given by the square root of the metric. I mean, these are all known facts, here specifically written for matrices. Another way to, I should just comment, this is just a comment, I'm not going to use it, just commenting, as was pointed out by Ali and maybe others many years ago, the metric can be factorized in this way. It's a positive definite, it's a positive metric. And in this case, the similarity is given by the matrix S between capital H and small h. And again, you have quasi-hermiticity as before. Okay, but this is not the case I'm going to discuss. I just, in my case, I'm just going to take the positive square root of the metric. Okay. So maybe some history, just very briefly, the term was invented by, or coined by Dieudonné many years ago in '61. It was published in a conference proceedings or that was held in Jerusalem before I was born. Another famous use of quasi-hermiticity, but without naming it, appeared a few years before in this paper by Dyson, which many of us cite. Here you see. Okay, so F is the metric. It's about spins, ferromagnets. And I should mention a nice paper by Andreas and Paolo Assis, where all this terminology and history and credits, etc., are explained in a very clear way. Okay. Now, I should also mention pseudo-Hermitian matrices. Pseudo-Hermitian matrices, if we relax the positivity of M, but keep it invertible, so the metric is indefinite, okay? There are interesting cases in physics where the metric is indefinite. For example, in Dirac's quantization, in Dirac's early attempts to quantize electromagnetism, you know that there are negative norm or zero norm states. Also, of course, the famous Lie model involves such states. And here, Pauli summarized the situation in '43 in this Rev Mod Phys. He didn't use the term pseudo-hermiticity. The term itself was apparently coined by Froissart, the guy from the Froissart bound, in a paper addressing this problem. Anyway, so I will, as I said, in the end of my talk, time permitting, I will show you some spectra of random pseudo-Hermitian matrices. They act, I should just mention that you can consider them as matrices acting on Pontryagin space, which replaces Hilbert space for the case of finite dimensional Hilbert space without, I mean, of indefinite metric, or in the infinite dimensional case, the Kranin space. Anyway, so I don't want to spend more time on this. Now back to strictly quasi-Hermitian. So H has to be of the form AM, where A is Hermitian. Sorry, I'm still in pseudo-Hermitian. So in the case of pseudo-Hermitian, H equals AM is still the solution. where A is Hermitian, despite the fact that M is not positive definite. And because square root of M is no longer Hermitian, and therefore, small h, which is the square root of M, A square root of M, can possibly be non-Hermitian as well. I mean, it can still be Hermitian if the phase is just, if it's pure imaginary. So squaring square root of M and square root of M gives you a -1, which is real. But in general, it can possibly be non-Hermitian, and in that case, the spectrum of small h will not be real. So, or alternatively, in this case, you will not be able to factorize the metric in this form, with all the problems arising. So, as I just said, the spectra of pseudo-Hermitian matrices can have or may have pairs of complex conjugate eigenvalues, and that follows because M is still Hermitian, so that the characteristic polynomial of H is still has real coefficients, and therefore roots are the eigenroots are either real or come in complex conjugate pairs. As a nice example of pseudo anti-hermiticity, which is pseudo-hermiticity multiplied by an I, is offered by generators of the non-compact orthogonal and unitary groups, for example. Okay, so let's say we live in a Minkowski space of indefinite metric of types n and m. So the metric has n pluses and m minuses. So in the real case, we are dealing with the orthogonal group O and M, whose defining relation for the group elements G is given by this. So near unity, the generator epsilon, they fulfill this anti-intertwining relation, okay, whose solution is epsilon equals AM, where A is anti-symmetric, real anti-symmetric, okay? Similarly, for the non-compact unitary groups, the defining relation is given by this. And the generators follow this anti-intertwining relation with solution epsilon equals AM with A anti-Hermitian. Okay, so you can use pseudo-Hermitian random matrix theory by drawing at random one of the generator and ask of either ONM or UNM, and ask what is the distribution of what are the eigenvalues? I mean, so you consider this as an ensemble. The generators form an ensemble of matrices, and you can ask what is the distribution of eigenvalues in this ensemble. So the plots that I will hope to show you in the end answer precisely this question in the large NM limit. And so Roman and I finished a couple of years ago some calculation which have to be written and put out on this problem, and that's the source of the plots I will show you. We have analytical and numerical results, and they match perfectly. I will show you only the numerical plots if time permits. Okay, so now let's go to the mechanical problem, which realizes strictly quasi-Hermitian matrices of small oscillations in a very nice way. Okay, so everybody knows the small oscillation equation for n-dimensional, for a system with n degrees of freedom. Okay, so M is the mass matrix. It has to be positive because masses are positive. K is the matrix of spring constants, or if you like, the Hessian of the potential near the minimum, near the stable minimum, about which small oscillations execute. The system executes small oscillations. The Lagrangian for the system is given here. Okay, so you have a metric A. It's strictly positive definite because it's a metric. This is the kinetic energy. And this is the potential. Q naught is the equilibrium point, and X is the small deviation from equilibrium. So the mass matrix is just the value of the metric at the equilibrium, and K, as I said, is the Hessian of the potential at equilibrium. Both these matrices are positive definite by definition, and the assumption that minimum is stable, that equilibrium is stable. Okay. So as you know, this is standard. We look for harmonic solutions for the equation, and we substitute this ansatz where A is the amplitude, omega is the frequency, and we end up with this eigenvalue equation, eigenmode equation. And you find it. You find the roots by looking for the zeros of the characteristic polynomial. Of course, all these roots must be positive, because if you look at the equation, assuming omega is a root and A is a amplitude, then you see that omega is the ratio of two positive quantities, and therefore it has to be positive, which is the case since we are dealing with a stable system and the frequencies must be real. Okay, there is no dissipation. Another way to see positivity of eigenvalues omega square is to rewrite the equation, to rewrite this equation here in this way, by shuffling around square roots of m in this way. So it's essentially a similarity transformation. And then you see that omega square are the eigenvalues of the matrix small h here, which is manifestly positive definite, because square root of m is Hermitian and k is positive definite. Okay. So as I said, square root of m, I take the positive root among all 2 to the n possible square roots of m. So I just put, for concreteness, I just take the positive one. I think I already said that. Anyway, yet another way to rewrite our eigenvalue equation, and now I come to the point of quasi-Hermitian matrices. So it's write it like this, okay? So the Hamiltonian, which we want to diagonalize, is inverse m times k. Its dagger is k times inverse m, which are not the same because k and m do not commute. Okay. However, H is strictly quasi-Hermitian with respect to the metric M, because it fulfills the intertwining relation. Okay. And this common value is just K, which is, of course, Hermitian. Okay. So H and H dagger are similar. H is strictly quasi-Hermitian. It is similar to this small h matrix. And therefore it's small h is Hermitian, and therefore the spectrum of H must be real. Moreover, because of the specifics of this problem, it's also positive, not only real. So this is general and doesn't have anything to do with randomness. Now let's introduce randomness, because I want to talk about non-Hermitian. I want to talk about strictly quasi-Hermitian random matrix theory. So imagine a very large mechanical system. N goes to infinity. N is very large. So complexity-wise, the system is very complicated. With high connectivity, every degree of freedom is connected to any degree of freedom is connected to any other degree of freedom. So all mechanical, all coordinates are coupled to all other coordinates, and all momenta are coupled to all other momenta. So obviously, this naturally lends, this problem lends itself to analysis in terms of random matrices. And now we have to decide what is the ensemble of these random matrices. So of course, we assume that M and K are uncorrelated, because M comes from the metric, the geometry of the system, and K comes from the, well, they may be related, but we neglect any such correlation. Okay, let me put it this way. And so I draw them from uncorrelated and positive definite ensembles. And then I compute, then I consider the random matrix H equals inverse M times K, and want to study the average spectrum of that matrix. The problem is that M and K are not commuting. Okay, M and K are not commuting. This is a big problem. Now, under some circumstances, we can overcome this problem by using a machinery called free probability theory. Okay, and in particular, there is an instrument called S-transform, which is part of free probability theory, which will help us solve the problem. Now, what is free probability theory? Free probability theory is an extension of ordinary commuting probability theory to the case of non-commuting variables. Okay. So in ordinary probability theory of commuting variables, when you have two independent positive definite variables, x and y, let's say, and you want to study the distribution of the product xy, there is a way to analyze this problem. What you do, you take the Mellin transform of each of the probability distribution function of each of the variables of x and of y. You multiply the Mellin transforms. I don't want to get into definition, etc. Don't want to spend too much time on that. So, but it's clear. I mean, everybody can play a little bit and see that what I'm saying is correct. So you multiply Mellin transforms, and then you transform back from the Mellin plane to the original variable, and then you will find the PDF of the product. Okay. So the S-transform method is the non-commutative analog of this very standard thing in probability theory. Of course, I'm not going to give you any details about free probability analysis, because it would take a lecture or an entire lecture or two. I'm going just to show you the results and then maybe make some comments later. So, but before that, I wish to make some remarks to put the problem in context. So, as I said, in the present work which I talk about, M and K are full matrices, random, positive definite, and statistically independent. This is to be contrasted with some classical work, very old classical work by Dyson and Schmidt, which in the 50s they analyzed atomic chains, random atomic chains. They wanted to study the spectra of phonons in random chains. Okay, harmonic chains. Okay, so it's a one-dimensional crystal, but with disorder. In a crystal, atoms interact with nearest neighbor interaction. So it's the springs that connect the atoms, which are fixed, I mean, at equilibrium, are located at the lattice point. So the matrix K, which encodes this nearest neighbor interaction, just xi minus xi plus 1 squared times K. Okay, so you have a spring constant and a harmonic potential depending on the difference between xi and xi plus 1. So it's a nearest neighbor interaction. In that case, K is 3 diagonal. It's a Jacobi matrix. So you have a diagonal and 2 off diagonals. It's 3 diagonal, very sparse matrix. And M, the mass matrix, is diagonal, just diagonal, because atoms, each atom has its own kinetic energy, and they don't talk to each other through kinetic energy, only through the potential. So the M matrix is diagonal. So K is 3 diagonal, M is diagonal, very sparse, and the basis dependent. Okay, it's very important to work in the basis of in the vector basis of the positions of atoms. Whereas in our case, there is unitary invariance. I will show you in a minute. There is unitary invariance, so bases can be rotated. There is no preferred basis. Whereas in Dyson and Schmidt, there is a preferred basis in which K is 3 diagonal and M is diagonal. So these are very old works, a bit, oops, sorry. A bit more recent work from 7 years ago by Schmidt, Kotos, and Shapiro. Boris Shapiro is my colleague in Technion. They studied heat transfer in some disordered mechanical system. But so that's the reference. And in their case, M was just proportional to the unit matrix. All masses were the same, and the matrix was diagonal. K, the matrix K, was random and full. So in this work, you could just apply standard methods of random matrix theory, because you basically have to deal only with one Hermitian matrix K. In our case, in contrast, M and K are full, random, positive definite, non-commuting, statistically independent matrices. So that's more complicated. Okay. So what did Roman and I do? What did we do to tackle this problem? So first of all, you have to choose an ensemble for the positive matrices M and K. So applying Occam's razor argument, that the simplest, perhaps simplest such ensemble is to assume that M and K are basically real matrices of this form, where C is a non-Hermitian general n by n real matrix, not with any other restriction, that what called real Ginibri matrix. And then you form this V-chart, what we call V-chart matrix C transpose times C, which is positive. However, it's easier for technical reason. It's easier to work with complex Hermitian matrices. Of course, M and K, by definition, in the mechanical system are real. But for technical convenience, we relaxed reality of C and allowed ourselves to use complex matrices, complex Ginibri matrices, n by n. So C1 and C2 are just complex n by n matrices, and we form K as C1 dagger C1 with some variance sigma K square, and M as C2 dagger C2 with some variance sigma M square. And in addition, we shifted M by a positive quantity M naught, because C dagger C might still have 0 eigenvalues, and we wanted to avoid that. We wanted M to be strictly positive definite. So we have to introduce a shift parameter M naught. So in essence, there are 3 parameters here: the variance of the K matrix, the variance of the mass matrix, and the shift M naught. And each of these matrices is taken Gaussian. This is called a Ginibri ensemble. C dagger C is a V-chart matrix, and when you draw C from this ensemble, this was first discussed by Jean Ginibri in 1966 or 63, I forgot, many years ago. And then we compute averages in this way. So this is the probability distribution, and F is the observable, and integration is just Cartesian integration over real and imaginary matrix elements. Okay, so I indicate such averaging by Bryant Cat with indicator with index sigma. Okay, so sigma indicates the ensemble. That's the idea. So in this business, what you have to do is to compute the so-called average resolvent, or Green's function. So we need the Green's function of the matrix H. I remind you, the matrix H is inverse MK, inverse M times K. So we compute the average indicated here over both sigma M and sigma K of the Hamiltonian inverse M times K. Okay. H is given by, as I said, inverse M. This is M. This is inverse M. This is K. And the density is found from the discontinuity resolvent. The resolvent is, well, we know that inverse MK is strictly quasi-Hermitian. So despite the fact this is not Hermitian, the eigenvalues are real. All the eigenvalues are real. And therefore, G is non-analytic only in the large n limit. Well, for finite n, it will have poles. It will have poles on the real axis, n poles, exactly n poles on the positive real axis. When you average, these poles start moving. So we will get, they will, on average, they will form a cut. And in the large n limit, the cut will become very sharp and definite. So in the large n limit, this resolvent is analytic except some cut, finite cut along some segment on the positive real axis, but is analytic everywhere else. So the density is, well, which is the average of the delta function here. That's the density by definition, density of eigenvalues, where z equals omega square. Okay, so these are our eigenvalues. It is obtained from the Green's function, from the resolvent, by computing the discontinuity of the resolvent across this cut. Okay, so it's given by the imaginary part of the resolvent. Let's say we come from a little bit below the real axis, and compute the imaginary part, divide by pi, and then we get the density. This is very standard. This model has some scaling relations that we can use for our convenience. So you can play with the parameters and see that the ratio of variances just factors out. I mean, you can factor it out from G and work with a standardized resolvent, which depends on scaling variables zeta and mu, where zeta is given by this is the rescaled z, or if you like, z over omega naught square, and mu is this quantity, m naught divided by the variance of the matrix M. And okay, and sigma k square over sigma m square is the ratio of like k. It's like k over m in ordinary when you teach your students about the harmonic oscillator with spring constant k and the mass m. So k over m is omega square naught. Sigma k is like the square root of k, and sigma m is like the square root of m. So this gives you a scale of a frequency scale dictated by the ensemble. Okay, so sigma k and sigma m are not important separately, but only as the ratio. And similarly, m and sigma m are not in the they do not appear independently. They appear through this combination mu. So obviously, it's better to analyze this standardized resolvent, which we call capital gamma of zeta and mu. So zeta is the rescaled z, and mu is the rescaled m naught. Now, as I said, free probability theory is very technical. It's not a talk about random matrix theory as such. I don't have time to explain it. So I'm just telling you what is the result. So from free probability theory, I obtain a cubic equation for the resolvent gamma. Gamma is the standardized resolvent, and zeta is the rescaled z. So we obtain a cubic equation, which we have to solve. So we reduce the problem to solving an algebraic equation, sorry, for gamma. Okay, and of course, there are three roots, and there are cuts and Riemann surfaces, and the roots intermingle and flip from one root to the other at the cuts, etc., etc. But anyway, we are looking for the global root, which behaves for large zeta like 1 over zeta. Why? Because let's go back to the definition of the resolvent. You see, it's 1 over z minus h. So for very large z, you can neglect the matrix. The trace gives you n. It cancels with this n. So you just get 1 over z. And therefore, in the rescaled problem, you should just look for the root that goes like 1 over zeta for large zeta. And there is only one such root. And I'll show you the properties of this root. Okay, so first of all, what we find, I remind you again that the density is supported only when there is an imaginary part near the real axis. There should be a cut on the real axis where the eigenvalues condense in the large n limit. So the poles of H, the eigenvalues of H produce poles, and these poles are confined in a finite segment. In a finite segment, in the large n limit, the distance between consecutive poles goes to 1 over n. Okay, since the segment where the poles live is finite, in the large n limit, they form a continuum of poles, which is a cut. Okay, so we are looking, and the cut is the imaginary part of G near the real axis, on the real axis. So it turns out that from
sorry,
yeah?
Joshua, where does the third order equation come from?
Oh, welcome. Yeah, it comes from free probability theory. I said I don't have time to discuss it because it's very technical and complicated. So for Andreas, I just repeat what I said. So we have two non-commuting matrices, M and K, which are positive. In my case, they are random matrices, independent, positive, and independent, non-commuting. So, okay, and now you look for the density of eigenvalues of inverse M times K. It's the product of these two non-commuting matrices. Okay. Moreover, in our model, in Roman and mine model, M and K are taken from probability distributions which have unitary symmetry, the so-called Ginibri ensembles. So for such matrices which are independent and obey unitary symmetry, you can apply a branch of non-commutative probability theory called free probability theory, which allows you to find the probability distribution of the product of these two non-commuting variables, independent but non-commuting variables. And as I said, it is the non-commutative analog of a well-known fact in commutative, ordinary commutative probability theory, in which case, if you have X and Y, two independent positive definite random variables, each with its own probability distribution function, you can ask what is the probability distribution of the product. Okay, so as you may know, what you have to do is to Mellin transform each of the PDFs of the probability distribution functions, multiply the Mellins, and transform back to ordinary space. It will give you the probability distribution of the product. And free probability theory is a non-commutative analog of that. Okay, it's very technical and complicated. I don't have time to discuss it. It's another talk by itself. Okay, so that's the logic that we follow, and that when the dust settles, it settles in a very nice pattern, and that's this cubic equation for the resolvent. So gamma is a resolvent, zeta is a complex variable, and we look for the solution of the cubic, which has this behavior because it is a resolvent of this type. So for large z, it just goes like 1 over z, and zeta is a rescaled form of z. So it should. This is the root of the cubic that we are looking for, and there is only one such root. So as I said, the cut along which the eigenvalues live, the support of the density, is finite. It lives between 0 and x1, x is the rescaled z, is the real part of rescaled z. So it's omega over omega naught squared. Omega naught, I remind you, is the scale set by the two variances, sigma k and sigma m. And it is a function of mu. I will show you I will flash for you the equation for x1 of mu. And you see, for large mu, the segment along which the eigenvalues live shrinks. And for small mu, it expands, okay? So here is the expression. It's really ugly, complicated, but it's only a function of mu. So psi1 is this complicated function. Delta, this discriminant, is another function of mu. And for large mu, x1 of mu vanishes like inverse mu. And this inverse mu behavior is more or less should be expected because omega square is essentially an eigenvalue, is an eigenvalue of inverse m times k. And this should go like inverse mu. For large mu, you can ignore everything else, so you should go like inverse mu. Okay. Oops, what happened? Oh, my PDF file disappeared. Just a second. What happened? Oh, what happened? Let me try to get it again. Ah, here it is. Okay, so for large mu, the segment where the eigenvalues live shrink. So the frequencies become very small, between 0 and a very small cutoff. You must remember this for later. How am I doing on time? Oh, I have how much time, Francisco? About quarter of an hour?
Yes, usually this is more or less the time that we're. Yeah.
Okay, so, okay. So maybe I should, okay. So we also know the density. Okay, so the density, I will show you in the next slide, the explicit expression for the density, but I should mention that for small density, for small frequency, x, I remind you, is omega square in units of omega naught. The density goes like inverse of square root. And for large frequency, near the end, near the high frequency end, the density vanishes like a square root, which is a typical thing in random matrix theory. And this square root singularity for complex matrices, for Hermitian matrices, sorry, for complex matrices, it indicates that there should be universal behavior, which you can see here, these oscillations of the blue line, for example. They are called Airy oscillations, and they are known from the Gaussian unitary ensemble. Here, of course, we don't deal with the Gaussian unitary ensemble. We are dealing with two Ginibri matrices. Yet, due to this universality, this oscillation appear. These are finite n oscillations, and they occur as the system tries to approach the asymptotic large n regime. So the large, you see here, the graph here with various colors. I don't want to get into the details. All the colors fall on each other. This is the density of eigenvalues, starting from 64 by 64 and all the way to 10,024 by 10,024. So you see they nicely fit on each other, and they only start deviating towards the high frequency end. You see there is some dispersion, and here is the inset is a magnification of the edge behavior, the high frequency edge behavior. So you see the smaller n, the more manifest the oscillations are. And as you increase, for example, you go from blue to purple, the purple you can see maybe here a little bit of the purple here. The oscillations are very small, you can barely see them. And they all match together with the large n. The large n limit is given by the dashed black line. So you see they converge to the dashed black line. The red line is the real matrices, the real Ginevrian matrices. They don't oscillate, and that's also known in random matrix theory. There are no such area oscillations for the Gaussian orthogonal ensemble. So this universality manifests itself here too. And you see very nice convergence to the large n limit given by the dashed black line. Okay, so for what it was, this is the monstrous expression for the density. We know it explicitly. Okay, maybe I shouldn't spend too much time. Maybe a few words here. At large mu, for large mu, namely large m naught compared to the variance of the fluctuations of the matrix C2, m becomes just proportional to, I can neglect the randomness, and then m is just a unit matrix up to factor m naught. In this limit, we are dealing with only one random matrix, K. And this matrix K, which I remind you is of this Wishart form, or C1 dagger C in the exponential, its eigenvalues is well known. It's called the Marchenko-Pastur distribution. And indeed, analytically as well as numerically, we see that that's the yellow line here. That's the yellow line for very large mu. Very large mu means very small variance of m, sigma m. That's the yellow line here. And you see the dotted. There is also a dotted line. There is the dashed large n limit, and also a dotted line which you can barely see. Maybe you can see the dots between the dash, like the Morse code. But here you see some dots. The dots are the Marchenko-Pastur analytical expression, and you see that the yellow line, which is the numerical result, follows the Marchenko-Pastur for large mu, as well as our analytical solution of the matrix model. So this is expected, and it's a nice check. Maybe I should skip this. I don't have time. I should spend some time on this. In our model, eigenvectors, we have unitary symmetry. So if you draw a matrix, a pair of matrices M and K from the respective ensemble, form the matrix H, which is inverse M times K, and then use a unitary rotation of both M and K, you will get an equally probable H from our ensemble. So the vector basis on which these matrices work or act is not important. Only what is only important are the eigenvalues. All bases, there is a complete democracy of bases. They are all equally probable. So, but the eigenvectors is the profile of the amplitude. It's how the individual atoms in the mechanical system like to oscillate. So, since no vector is better than any other vector, they must all be extended. So all atoms participate in the vibration in this highly connected, because everything is connected to everything else. No part of the system can stay still while the rest is oscillating. So in this model, all eigenvectors must be what we call extended. And a measure of localization or extendedness of the eigenvalues is offered by what Franz Wegener invented and called normalized participation ratio. This is this object. So AL is the n-component amplitude vector. You take a normalized vector which is normalized to 1. You compute the 4th power of each component. You sum them, invert, average over the ensemble, and divide by n. If this quantity is of order 1, then argue immediately that the eigenvector is extended. If it is a small fraction of n or goes to 0 in the large n limit, it is a localized eigenvector, meaning only small part of the system vibrates. So these are the numerical, this histogram, these are two histograms. The blue one is for complex matrices, and the yellow one is for real matrices. And you see that and the graph here in red is the spectrum, just to indicate it has nothing to do with the measurement. It's just to indicate for you the frequencies varying left to right. So you see we bind the for each eigenvalue we computed P of omega squared for that particular vector, and then we bind them into this histogram. So you see the histogram is flat at half for the complex matrices, for the complex model, for the complex matrix model, and is flat at 1/3 for the real orthogonal matrix. And in the standard random matrix models, the GUE, Gaussian unitary ensemble, the Hermitian random matrices, and the Gaussian orthogonal ensemble, the real symmetric Gaussian matrices, you can compute these participation ratios. GUE gives you 1/2 in the large n limit, and GUE gives you 1/3 in the large n limit. And lo and behold, also in our model, we get the same values, So this is to be expected. And this is a quick argument to what I said before. So let's say you have an extended normalized eigenvector. So typically each component is 1/√n because it's normalized to 1. And then you can compute P, you get something of order 1. If, on the other hand, you take a localized eigenvector, where typically it's the amplitude is non-zero only on some set of L sites in the system, then you can again perform this exercise, and you see that the participation ratio is L/n. If L is finite and n goes to infinity, this should go to 0. So this is a good indication whether eigenvector is extended or localized. And in our matrix model, everything is extended. Now, as in the textbooks, given a harmonic system, you can ask about the phonon spectrum or the thermodynamics of this system. So we computed the equilibrium thermodynamics of our mechanical system, the average energy. So you take the density of frequencies. The density of frequencies is obtained from the density of eigenvalues omega squared by this, in the obvious way. And then you smear it against the average energy per mode. Yeah, so this is the oscillator mode. Each mode is an oscillator mode. Oh? And then you integrate. If you divide by n, you get the energy density, if you like. And also you can compute the specific heat. So these are the results. For example, this is the energy. This is beta. The horizontal axis is inverse temperature, beta, Boltzmann's beta. So this is high temperature. All curves, they diverge like inverse beta. This is just equipartition. And here you see they flat out for low temperature. This is just the 0-point energy of the system. And of course, it is fixed by the scale of the width of the band of eigenvalues. So, for example, the purple one here corresponds to the largest mu. Largest mu means very massive particles. Very massive particles, they oscillate very slowly. And for large mu, as I told you, the bandwidth goes like inverse mu. So we are dealing with very small frequencies, and therefore you get a very small 0-point energy. Likewise, in the specific heat, you see for a large temperature, again, it goes to kT. That's the one here. And for small temperature, in the ground state, it goes to 0, but at different rates. So the purple line here again is very large mu. Very large mu means very small frequencies. So it relaxes to 0 very slowly because it only has very soft phonons, as opposed to the blue line, which has many high frequency modes. Okay, so everything makes sense. Now I only have a few minutes left. So I want to mention here very briefly some theoretical results about vibrational spectra of proteins. So Michael Levitt, who used to be in the Weizmann Institute and now is in Stanford, is a Nobel laureate for chemistry a few years ago. He did arduous work of actually analyzing the potential energy surface of these macromolecules. And then his postdoc students at that time, from the landscape of the potential, he computed. He did exactly what I did before with the small oscillation expansion, and computed for each macromolecule. There is a database stored somewhere. There is a international database on various protein molecules. So you get for each molecule, you get the landscape of the potential. From that, you can compute the frequency, the spectrum of small oscillations. And what these two people did, Ben Avraham and Monique Thirion, now in, I guess, upstate New York, Potsdam, upstate New York, they analyzed the statistics of this spectra, and they found that there was some universal behavior for small frequency, namely the small frequency, meaning the collective vibrations of the big chunks of the molecule. They oscillate together. Big chunks are heavy, so it's very small frequency. And they found that in all those globular proteins are proteins which are tightly packed, very tightly packed. So a protein is a line, is a chain of amino acids. It can contain from few dozens of amino acid monomers to few hundreds, and it is packed highly packed into a globulus. And so even molecules which are far apart on the chain can interact through hydrogen or electrostatic interactions. So the connectivity should be higher than just nearest neighbor. And the collective modes, they found invariably, all the spectra have this, what looks like a universal behavior. So our result may somehow explain this or not, I don't know. That's something we are thinking about. And well, we also analyzed this pendulum. I don't have time to discuss this, but after I will give you the file, so people could. I mean, we have some nice. That's another realization of a full mechanical system. So you know the single pendulum. Everybody knows the single pendulum. You may know that the double pendulum is chaotic, and here we went completely crazy and consider a pendulum made of n segments, which is the discretized version of a string, some mechanical string made of these segments. The segments are rigid; they cannot stretch. So this is a string of fixed lengths, and then we put all the mass. We neglect the mass of the rods of these segments and put the mass at the endpoints. And also at the endpoints, we put charges, like charges, to have a Coulomb repulsion. So each point here is a mass, including the suspension point here, which is fixed, has a mass and also has a charge. Okay, and then you let and everything is suspended in Earth's gravity, and you study the vibrations of this, or oscillations of this thing. M and K could be found to be full matrices. Believe me, I mean, maybe you cannot absorb it from here, but they are full matrices. And the bandwidth goes like n squared, and here are some numerical and analytical results. Here are some eigenvectors. You see an extended eigenvector, another extended eigenvector, a localized eigenvector. You see only part of the string oscillates. I don't have time to dwell on this. You will, well, it will be on the website, so you could take a look. If we make the system ordered, clean, uniform, chargeless case, let's say set all the charges to 0, make the segments uniform, so you can work out the continuum limit, and you can transform the small oscillation problem into a partial differential equation. Okay, and you can solve it. That's the eigenstate. It is given in terms of a Bessel function, and there is a spectral condition. The eigenmodes are given by the zeros of this Bessel 1. Omega naught is this G over L, the well-known expression. And this is, in a sense, for those of you who are familiar with, it's in a sense a classical realization of a Stark ladder in atomic physics. So we analyzed the analytical, we present here the numerical results for the eigenmodes versus the analytical results. The dots here are the solution of the Bessel 1, and the red line is the numerical diagonalization of the discrete system for very large n. The blue line is for a smaller n, for a quarter of that. And you see that the small frequencies agree very well, as you know. When you take a tight binding approximation for an electron in a solid, near the minimum of the energy, where the energy is given by cosine of k, near the minimum of the energy, you get a parabola. So the continuum free particle spectrum agrees with the tight binding, and the same thing happens here. So the small frequencies or the continuum limit, they agree very well with the discrete version. Here is an eigenfunction. And maybe I should just flash a few pictures of eigenvalues of pseudo-Hermitian matrices. Another paper Roman and I finished. So again, there is a indefinite metric with k pluses and n minus k minuses. K over n is finite. We assume k over n is finite. It's a finite fraction, lambda, between 0 and 1. What we find, both analytically and numerically, I'm not going to show any analytics. I just just show you the numerics. But what we find is that eigenvalues live in blobs, in two-dimensional regions in the complex plane, of course, in a symmetric configuration with respect to the real axis because of pseudo-hermiticity. So they come in complex conjugate pairs. And okay, and also there are eigenvalues on the real axis. So the spectrum is always mixed. Part of the spectrum is in the complex plane and part of the spectrum is on the real axis. We know the density and the shape of the blobs in the complex plane, and we also know explicitly the density on the real axis for in the large n limit, of course. Everything is in the large n limit. Here is the fraction of the real eigenvalues given lambda. So you see lambda equals half where half the matrix is plus and half the matrix is minus, is devoid of any real eigenvalues in the large n limit. But for small lambda, of course, all eigenvalues, almost all eigenvalues are real, because then the problem is essentially Hermitian. So here are some numerical results. You see for the same lambda, increasing the size of the matrix, but keeping lambda fixed. You see there are various number of samples. So you see two blobs in a symmetric, organized symmetrically with respect to the real axis here. And you see that as n is increased, the noise gets smaller. And you see the eigenvalues occupy a more definite region surrounded by this boundary, the black line. We know the equation of this black line explicitly. And in the large n limit, everything will reside inside the black line and with uniform density. And of course, you will get some density on the real axis. And this is the same picture for yet larger n, much larger n. And you see almost no observable noise. Self-averaging, essentially. It's a very big matrix. Everything is self-averaging. You just need one case. Very nice, definite blob inside the theoretical boundary. And this is the case for lambda equals half. So you see almost no real eigenvalues. Again, for very large matrix. Uniform density inside a unit disk, which is similar to Ginevri's spectrum. And this is the spectrum on the real axis for various values of lambda. We know the black curves analytically, and you see the histograms of the numerics, so everything matches. And yeah, I should mention that these results were obtained using the diagrammatic method. Use Feynman diagrams for the matrices using double lines, because matrices have two indices, unlike vector particles. So you need double lines, and in the large n limit, these double lines, you can construct surfaces with them because they are oriented. And in the large n limit, only planar or spherical geometry survives the large n limit. And then you can resum these diagrams explicitly using standard tricks of quantum field theory and obtain explicit results. So this is the diagrammatic method. And Roman, in his talk in a few weeks from now, he will discuss an avatar, a more interesting version of this model. Here I just had a fixed metric, indefinite metric P with +1s and -1. In the model Roman will discuss, there will be a parameter here, T. So you will have a K pluses and T and n minus K entries, which are T. The metric is diagonal, but there is a parameter T, which starts from being positive, goes through 0, and then goes negative. So there is a transition by parameter from strictly quasi-Hermitian to pseudo-Hermitian, and it reveals a wonderful system of phase transitions. Eigenvalues start migrating from the real axis to the complex plane in a very, very nice way, and that will be part of what Roman will talk about using the diagrammatic method. So I think I should rest now. I took 10 minutes. Sorry, nobody stopped me. Okay, so if there are any questions or comments.
Thank you very much, Joshua.
Thank you for your patience.
Is there any question, comment?
I must have been so clear.
You have any main conclusions left, Joshua?
Conclusions. Well, first of all, it's obviously an interesting set of models. In the model which Roman will describe, we have partial results. He will describe them. We also wish to study. Well, you know, for example, in the cubic PT. Excuse me. In the cubic PT model IX cube, there is a problem with the metric. The metric is singular. It's not invertible, and that is a problem. And as you make epsilon in the Bender-Bottcher, or nu, I think the exponent nu in the Bender-Bottcher family of potentials going smaller and smaller, you end up with metrics which become more and more singular, and then you start getting more and more complex eigenvalues. Essentially, I think the T model that Roman will talk about tries to mimic this behavior and find some universal behavior, at least from point of view of matrix models, which are in which you have the infinite Hilbert space cut into finite size, so you can tame some of the. I mean, you don't really need all the complications of functional analysis. You're only dealing with matrices, and maybe we can learn something about this transition. Well, another conclusion is that, as I said, this matrix model is potentially interesting with respect to a real physical problem, namely vibrational spectra of proteins, which is another direction we are looking into. So basically, it's a lot of fun. I mean, you can apply all these ideas from PT symmetry and non-Hermitian optics, etc., using matrices. And if anybody has a model, a system he wants to model with a random matrix, I'm more than interested to discuss it.
There is a question from Duncan. I don't know if you want to ask for yourself.
Yeah, please.
Hi there.
Hi.
I was wondering, so if in this example again of hanging connected pendula, where's the non-Hermitian behavior in that?
Okay. The non-Hermitian behavior is because of the inverse. It's the thing I defined in the beginning. It's the inverse m times k. Okay. Where was it? Yeah, I think. Just a second.
I was thinking physically.
No, physically it is Hermitian, but no, it's just mathematically, because here you see the matrices we are dealing with. Yeah, we are diagonalized are non-Hermitian, H and H dagger. So I mean, but this is a very mild non-hermiticity because H is quasi-Hermitian. The spectrum is completely real and positive, moreover. However, for example, using this kind of machinery, you can study what happens when some of the springs start to get soft, and the case may start develop instability. So instead of a perfect parabolic minimum, you'll start developing in unstable directions, hyperbolic. So you can start fooling around with the inertia or the signature of K, and then you will move from quasi-Hermitian to pseudo-Hermitian, And that will really bring you non-hermiticity, because real instability will be in your system. You could analyze the spectrum of small oscillation in this system. I mean, of course, if you have an non-stable system, small oscillations is maybe not the most physical thing to happen, because unstable modes will grow, but at least before they grow out of control, you can at least study the system for very short times using this machinery of random matrices.
Can I ask another question?
Sure.
Does this SYK model?
Yeah, you mean
have you heard of,
in holography, the people who do holography?
well, yeah, I think it originated in condensed matter physics, where you have
generalization.
So you start with a highly connected system, where the idea is that you have highly connected everything, but disordered.
Yes.
So everything's interacting with everything.
Yeah.
And then it got picked up by the black hole community as something that scrambles information very rapidly and efficiently, and things like that.
I know about that.
Yeah, are your results relevant to that model?
Not directly, because there you have, that's a generalization of the so-called Sherrington-Kirkpatrick model of spin glass. In Sherrington-Kirkpatrick, you have a lattice. It's a Ising model, but with random bond and random exchange integrals, where everybody talks to everybody else. So it's not nearest neighbor, it's everybody talks to everybody else. And but it's only two spin interaction, okay? But in the SYK model, you add more. So not only two spin interaction, but now 4 spin interaction.
Full body
so
and things.
The couplings are now scaled differently, but in a way such that you have a good thermodynamic limit. And that's the next step. I mean, then you could study Derrida's p-spin model, or random energy, if you know random energy model, which is where you take infinite number of spins interact. It's like the p-spin model. So p equals 2 is the Sherrington-Kirkpatrick, p equals 4 is the SYK, and then p goes to infinity is the Derrida random energy model. So you could but there is no non-hermiticity there, or quasi-hermiticity. Maybe you can invent a model if there are 2 non-commuting matrices or tensors. Yeah, I think you could maybe, if you have 2 of them, if you have 2 such systems interacting, I mean, each on its own, and then both of them are interacting, then maybe you can apply this. But for that you don't have to go to SYK. It's enough to look at Sherrington-Kirkpatrick already.
Mm-hmm.
Same complications will arise there as well.
Mm-hmm.
Thanks. Let's take the last question from Mikhail.
Yes.
Mikhail, you want to?
Yeah.
Is with your hand rising?
I can't see. I can't hear.
I know. I see. Mikhail.
Could you increase your volume? I can't hear you. Mikhail. Yeah. Now I can see you. I can see you. Hi.
Hello.
I can't hear you.
Mikhail, we can't hear you very well.
No, I can't hear you at all. And I cannot read lips. Unmute your microphone.
He's unmuted. I hear him very...
very weakly.
Yeah.
Do you hear me?
Very little. It's not very loud.
Can you relay Mikhail's question to me?
Yes. Let's see.
If you hear him, can you relay the question to me?
Mm-hmm. Let's see.
Do you hear me?
Not very well, but maybe you can write down in maybe you can write down the question. Yes. It seems now it's better.
Do you hear me?
Yes.
Ah, yes, now I can hear you, yeah.
Joshua,
Yes.
We can hear you.
hello, do you hear me?
Yeah, I
Yes.
can hear you. I can hear you, yes.
Okay. Joshua, I have the phone question.
Yes.
In the way you looked at some chain of pendula, yes?
Yes, yes. Let me
Okay, and you mentioned their chaotic behavior, but is it correct? Is it correct that you at some point you also mentioned the limit case when the number of pendula goes to infinity and
Yes.
their length go to 0? Yes.
Yes, yes, that's the continuum limit.
Yeah, yeah, and in this limit, you obtain some continuous
Yes, equation.
chain,
Yes.
and its dynamics is described by Bessel function. Yes.
Yes,
First,
yeah, you get
yeah.
an equation.
Yeah,
Yes.
but
Differential equation.
so I'm confused. It seems that if you have the definite dynamics described by Bessel function, how or why chaotic behavior disappeared in this infinite limit? How to understand this?
That's a good question. Well, I think the chaotic nature in the double pendulum, I think it has to do when the two pendula, when the two masses and the arm lengths are different. So maybe I'm not sure. I'm not sure about that, but I think that may have to do with the chaos. Here, in order to get this continuum limit, I took all, you see, I took all segments to be the same, all masses to be the same, and then kept n to infinity, each segment to 0, so such that the length is fixed. So this is only for this very neat ordered limit, and indeed in this case all eigenstates are extended and everything is exactly solvable. But if you keep them random, each length on its own, each mass on its own, then you get localization. The amplitude becomes localized, and eigenfunctions, some of them are localized, other eigenfunctions are extended. So I think this Anderson localization of the amplitude, this is Anderson localization. I think the Anderson localization of the amplitude indicates that the classical indicates chaos in much the same way as in atoms on the line, or in the kick-trotter problem. Again, in the kick-trotter problem, as you may know, there is a relation between classical chaos, the Chirikov standard map. You know the Chirikov standard map? Are you familiar with the Chirikov standard map? So there is a relation between the kick-trotter and Anderson localization in the quantized version of that. I mean diffusion. I mean whether you have diffusion in phase space or not, and Anderson localization in the quantum version of that. So I think your question is very good to the point, and so I think the answer is that it's just a conjecture. I don't know for sure, but given on what I know, I conjecture or presume that this localization problem, this change from extended to localized eigenstates in the disordered system, where each length is random. I mean, there are random variables. The masses are random, the charges are random. So the Anderson localization transition there probably indicates chaos. In the case I flashed for the continuum limit, it was the perfect chain. The perfect chain is too perfect to be chaotic. I think that's the reason. But I will check. Let's check afterwards to see if the double pendulum for identical penduli, I mean, the two masses and the two lengths are the same. Maybe it's not chaotic. I don't know. Duncan, do you work with Berry? Do you know?
No, to my shame, no, I don't know. I should. I've studied the double pendulum, but I didn't realize it wasn't chaotic when you make the lengths the same.
Okay.
I hadn't heard of that.
Okay, so I don't know either. So, but my hunch is that it's not chaotic, but we'll check.
Okay, thank you.
Okay, thank you for a very good question.
I had a comment that when you consider Anderson localization in the localized regime, you get regular behavior. At least you get Poisson statistics, because when you get localized wave functions, each system, you get a lot of subsystems that behave independently.
Right. So, but we didn't study the statistics of eigenvalues, just the one-point function, just the density. That's I mean, it's complicated as it is already. That these are the various densities in various cases, with and without disorder. Okay, so the dotted lines are disordered, the full lines are the ordered cases. The yellow is just gravity, the blue is just Coulomb interaction, and the red is both. So, so when you add disorder, you start. You get the dotted lines. You see the gap in the spectrum closes. But more importantly, you see that eigenvectors can be either extended, less extended, or localized. Despite the high connectivity, this is a highly connected system. It's not a one-dimensional system. It's a highly connected system, and yet you get this either transition or a crossover. I don't know exactly what's going on there. If it's a real transition or a crossover, but something interesting that is going on. So we don't know everything, at least not from this preliminary at this preliminary stage. Okay. I see some more question. What is some on the chats?
No, so just
Okay,
Duncan.
So, people had to go. Okay.
So thank you very much, Joshua.
Just a comment.
Thank you for your patience.
Just a comment. I mean, in your introduction, Joshua.
Yes, I can hear you.
I always see that people suggest that the square root of a matrix is unique, but if you have
no, I said.
In your case, there are many.
Yes, I
said. Transform the square of a matrix. So in the PSEUDO-HERMITIan case, the square root of your matrix is completely not unique. So this should be taken into account when you.
No, I don't think it matters. It doesn't matter. Not for this system.
You never took here a square root, but at the beginning in the introduction, when
I'm looking. Yeah, here you're referring to this slide.
One always has the feeling there's only one phase of a Hermitian equivalent Hamiltonian. There is an infinity of different equivalents if you take a square root of a metric, and this makes the systems with many degrees of freedom so diverse. Yeah, but here everything is under control, and look, if you have a positive matrix, you just diagonalize it, and then on the diagonal, in the PSEUDO-HERMITIan case, where not necessarily everything is positive.
Okay.
Then you get a very diverse mathematics.
Yeah, I agree. But I mentioned this in the context of positive metrics. So in the context of positive metrics, it doesn't matter. Yeah, you are right, of course. Yeah, thank you.
Good.
Any other?
It seems not. So thank you very much, Joshua. Thank also to everyone.
Thank you for having me.
Yes.
Thank you.
May we please also ask you to send us your slides in order that we can.
Sure. Okay, we will be in touch about that. Okay.
Okay. So
thank you.
Thanks again, and thanks also to everyone. And see you next time.
See you next time. Bye bye.